Good afternoon. So I'm Venkatramani. I'm an assistant professor at Shivnadar University. So I'm also a PhD from this place. This is a work done by my PhD student Dheeraj, and it's in collaboration with Dr. Chandan Bose and Dr. Sirshendu Mondal. So the idea here is we want to study a specific class of nonlinear aeroelastic phenomena called as stall flutter from the point of view of synchronization. So why we want to study and what we encounter by doing that would be the broad crux of today's presentation. So let's see through that. And so to continue on, see, when fluid structure interaction occurs, there is a specific class of problems where you have flow separation occurring. And this is not a one-step process, but rather a multi-step process. And this multi-step process is often viewed as a nonlinear phenomena, a nonlinear aerodynamical phenomena, and in turn is called as dynamic stall behavior. And the output of it from a structural perspective, which is usually termed as stall flutter up here. And this is a very dangerous one, and it occurs in a number of systems ranging from aircrafts to wind turbine blades, helicopters, and UAVs. In fact, one of the best examples that's unfortunately not put here is the helicopter blade problem, which is the single largest incident of stall flutters that are occurring up there. So now what happens is, the physics of stall flutter is very complicated because the physics of dynamic stall, the aerodynamics itself is very complicated, and in turn the response dynamics therefore remains an unknown mystery on that regard. So what happens is the further complexities like nonlinearity, say for example in the structure, or if you are going to have some uncertainties, be either in the structure or in the flow field, can give rise to unpredictable dynamics as well as a real challenge towards the structural safety. So towards this, understanding what is this particular stall behavior in terms of aerodynamics and its aeroelastic output stall flutter is quite pertinent. So one thing that has happened so far in the literature is that they've used stall flutter as a 1 degree of freedom phenomena. That is, it is torsionally dominant and so forth. This has been the traditional understanding of this particular field. Despite knowing the fact that dynamic stall is nonlinear, stall flutter is often viewed as a single degree of freedom problem, where it is a torsionally dominant oscillation. But there have been, hints in the literature in the last decade where they're showing that the other modes, say for example, the bending mode, plunge mode as they call it, plays a huge role, but very little idea on what is the, impact on the other mode in stalling behavior is unknown. And given that most realistic structures have, are actually cantilevered wings and so forth, where other modal interactions also play a big role, it is pertinent to study what is going to be the modal interaction between the bending and torsion modes in an airfoil kind of problem when it is subjected to stall. Keeping this in the backyard, we have certain problems that we are going to address up here. What we want to know is, what is fundamentally the definition of stall flutter? Is it just simply that you're going to say it's a torsionally dominant oscillation and stop with it, or is there something more to say? And if there is going to be another definition that what we want to say, what would be the roots to instability that we'd want to state with it? And can we predict, or rather suggest, not predict, suggest some kind of physical mechanisms for this? Can we also underscore the role of nonlinearities and see to an extent on the stochastic wind? These are what we are going to see by invoking the concept of synchronization theory here. So what we do is, as we have said earlier, that this is a very complex problem. Mathematical models are available, but they're far from perfect and are themselves complex. So therefore, we go up to the extent of actually simulating stall flutter in a wind tunnel. So this is a patented setup of mine in which we simulate stall flutter at certain parametric conditions, and we do this in two forms. So that is what we are going to spend a minute to talk about up here. So what we do is, before we go on to that, I'll just explain what this setup basically does. You are basically having a wing which will allow you to through this mechanism where you can undergo bending, torsion, modal vibrations. And we can also introduce tailored amount of structural nonlinearities here that we want to. And we have an estimate on what kind of parameters would be used up here to introduce what is called a high angle of attack problems here, which is essentially stall. So what we do is we measure the vibrations through laser sensors. We also have air velocity sensors and hot wire anemometers throughout the wind tunnel sections to continuously acquire flow data in some sense. It's a very rudimentary way of getting the spatiotemporal flow data in the wind tunnel test section. And then we do the data acquisitions and so forth. But the crux of the problem comes over the fact that we do this particular form of stall experiments in two modes. One being in what is called the suction mode. How do I play this video? Once again. Yeah, in suction mode, wherein we have seemingly we have seemingly, deterministic flow, which is measured through the flow velocity and the confidence level that we have on the structural parameter, where you have a transition to limit cycle oscillations in the airfoil problem, which is essentially a half bifurcation problem where you have large amplitude limit cycle oscillations coming up, marking the onset of stall flutter. So the other problem that we do is we then let the wind pass through what is known as, one second, I'll just play this video. Through blowing conditions. Can you help me play this video, please? Because it seems to be not the second one. Yeah. Thanks. So we let the airfoil now vibrate up. We do the fluid structure interaction study upon, not having any kind of honeycomb meshes. Essentially, there is, tunnel noise, or rather the fan noise that drives the oscillations. In very rudimentary and very approximate sense, this is some kind of noise-driven oscillations that come up here. In fact, what we show here is noise-induced intermittency that comes where subsequent increase in the mean flow speed would lead to violent stall flutter from this, what we believe and perceive as stochastic stall flutter. So we have now two different set of data that we have up here, where we simulate stall flutter in a wind tunnel up from a so-called deterministic perspective, and we also simulate the stall flutter from or acquire the data of stall flutter up from what we perceive as noise-induced perspective. So in the, when we go upon the deterministic parlance, which what we see as noisy one will come a little later, we see that there is, a transition from, a fixed point behavior to a limit cycle behavior, which results in a coalescence of the flutter frequency with the pitch natural frequency, which is one of the canonical litmus tests for stall flutter, which is because viewed as a torsionally dominant oscillations. And we see also that the amplitudes are very high in pitch, which is again an indication of stall flutter. All right, but then, and this is about the bifurcation diagram. But one thing that we interestingly note, which is a very up and down point up in the literature, is the presence of subcriticality. What we do is there are two things that are done up here. You go upon a forward sweep where you increase the flow speed, and at certain thresholds of perturbations, you see that at the fold point, the system jumps to limit cycle oscillations. All right, it's again indicating the sensitivity to initial conditions. Alternatively, what we do is once we hit upon limit cycle oscillations in the absence of perturbations, we do a backward sweep, which once again shows the persistence of limit cycle oscillations up till the fold point. So now there is at this chosen set of parameters and the initial perturbations and the initial angle of attack that were taken into account and all that, there is some subcriticality as well present in the system. This is being said in a rather cautious manner because this is still a matter of debate in the nonlinear aeroelastic literatures, whether stall is indeed subcritical or is it an artifact of certain parameters and so forth. So we are cautious to say that at this chosen set of values that we have taken up here, it appears to be subcritical the way it usually is defined up in the literature. Given this, what we next do is we understand this subcriticality by saying that there is a sensitive huge sensitivity to what is called as perturbations. We show that for certain perturbations you continue getting a decaying responses, but whereas for certain larger perturbations you get continuous limit cycle oscillations at the same bifurcation parameter. Here the bifurcation parameter being the flow speed. All right. So this shows the rather hints or the presence of transient growth in a system. What we do is we do not show the numerical study up here. It's not a part of this presentation, but we cast the numerical model, linearize the overall equation, and show the presence of non-normality in that, which is a typical yet another yardstick for the presence of subcriticality in the system. But all this were remaining unknown in the literature, and as I told you, stall being multimodal or stall having 2 degree of freedom interaction itself is something that is just getting developed in the literature, and we are doing it here for the first time. So what we next do is, given that we are encountering, say for example, subcriticality, or we are having all this, say half point transitions and subcriticality and so forth, we need to understand why these things happen, or rather what is the interaction between modes in these in the phenomena that we are observing up here. Because once again, to reiterate your mind that stall flutter has been seen as a torsionally dominant oscillation. So what we do is we invoke the idea of synchronization up here. We estimate the pitch. We have shown here only the pitch mode data, that is the pitch angle data, but we have also the plunge data, the 2 degree of freedom data, and based on that we estimate or rather compute the interaction between these modes by computing the synchronization features. So for first thing what we do is we compute its relative phase values and then embark into getting the phase locking values. What we see in the deterministic sense, in the post-Hopf bifurcation dynamics parlance, is that there is a perfect synchronization, which is completely in, trends with what is there in the literature. It is completely a believable and making sense idea that post-Hopf bifurcation, there are large amplitude limit cycle oscillations that are coming up, and in turn, they are perfectly synchronized. But then you may recollect that earlier there were as well subcritical behaviors. This is in the deterministic parlance itself. So what we do is we go to the fold points and from fold to the Hopf point, and we see what happens up there. We interestingly note that there are epochs, or rather scenarios, where there are momentary phase synchronization, which drops by values of 2 pi, again having a momentary presence of synchronization, again dropping by 2 pi and so forth, which is essentially an indicator of intermittent phase synchronization present in the system called as slips. So we essentially observe some kind of phase slips in this behavior. All right, so from fold point till the Hopf point, we are observing phase slips, whereas post-Hopf point, we are having complete phase synchronization, mutual synchronization as it is called as. What we next, assuming that what we did in the blowing conditions is indeed what we call a stochastic flow, we had an noise-induced intermittency route to LCO transitions, and here it is a little more interesting to observe upon what is going to happen here, because intermittency is neither a fixed point type of decaying behavior nor a continuous limit cycle kind of response. Continuous in the sense it's neither a fully limit cycle kind of behavior. So you have an alternating dynamics present up here, and what we note is that when we have this kind of transitions where you have noise-induced intermittency, or what we call here as noise-induced random oscillations, to a transition to a seemingly stochastic stalled flutter, we have phase synchronizations which are really interesting up here. Initially, in the noise-induced random responses that we have, which are of much lower amplitude, we have very weak synchronizations, which is very expected. But as you transition to LCOs, we still see the persistence of asynchrony, where we specifically call them as epochs of phase locking and drifting. So you have some kind of noise-induced phase slip still present, which is largely due to the drop in amplitudes that we are getting up here. So the transition is not rather so clear that is happening from a noise-induced intermittency or oscillation to a noise-induced stall flutter that is happening up here. So what we do here is we show the PLV. We show that yes, when you have noise-induced random oscillations, there is some a lower value of PLV, which makes sense. And as you head towards large amplitude stochastic stall flutter, which is characterized by this more PDFs that we have shown here, there is an increase in the PLV, showing that probably there is some synchronization, good amount of synchronization. But in between, in the transition regime, there is a clear drop, which is due to a clear change in the amplitude levels that are there occurring in the system. So what we do up here is we take up the relative phase values and plot what it's called as waterfall kind of plots, where we show the probability density functions for it for various flow speeds. You can see that at low values of flow speeds, seemingly low values, you have a bimodal structure which are peaking around 0 and 2 pi. Alright, showing some kind of coherence or synchronization between the peaks. As you increase the mean flow speed, we are encountering the random limit cycle oscillations as we see here. Alright, the random limit cycle oscillations by the loose definition up here would be called stochastic stall flutter. You see that the peak shifts towards pi, which is essentially a shift in the peak synchronization behavior, which is called as phase flip kind of behavior. So we are encountering perfect phase synchronization, phase slips, noise-induced phase slips, and now a phase flip behavior as well coming up here. Again, showing that the interaction between plunge mode is not so trivial that can be ignored that as it is typically happening in the conventional literature. So through this, what we have two major findings that came, two papers that came out. For further details, you can refer to it. Both are two chaos papers up here. And we next proceed up to so these are the interim summary that, whatever I just told you some time back. But what we are noticing in recent literatures is that you have more atypical phenomena coming in stall behavior, especially in 2 degree of freedom stall behaviors, which essentially shows that, as I mentioned a few times before earlier as well, that the structural parameters and what is called the initial angle of attack is a very sensitive parameter up here. So we have, limited idea about it because we are doing experimental studies and not a numerical sweep. But then as one step higher than what we have done so far, we embarked into studying structural, the effect of structural parameters by tweaking slight things in the experiment. What we did was essentially, as of now, the structure is linear, but the aerodynamics is non-linear. We next proceed to have a scenario where the structure as well becomes non-linear. So you have non-linear structure, and the aerodynamics is dynamic stall, which is as well non-linear. And we see some very interesting, behaviors in the wind tunnel, which I'll show you up here. So you see that at low flow speed, the fixed point responses get transformed into limit cycle oscillations, which is typically what you call as a Hopf bifurcation behavior. Increase in flow speed has a growth in the amplitude, which is once again a known phenomena. So you have violent stall flutter oscillations coming up. But then interestingly, we start getting an intermittent period 1, period 2 switching at the post-Hopf dynamics. Remember, this is all in the deterministic scenario. The more we increase the flow speed, we see more violent oscillations coming up for stall behavior, which is typically happening in helicopter blades and wind turbine blades kind of structures, which transforms into a beat type behavior at the final flow speed that we could encounter. We could not go higher than this because the structure could not withstand the vibrations. The springs could never withstand the vibrations greater than this. So now clearly, this is something that we are having to re-emphasize an atypical route or an atypical instability scenario that's coming up here. Though it is seen in different terms and terminologies in the literature, I just said some time back that idea of beating and other mode dominance is not so uncommon, but people are just realizing it. We also had an interesting observation that not just our structure was non-linear and the aerodynamics is non-linear, but the structural frequency ratio, that is the plunge to pitch uncoupled natural frequency ratio, is 0.44, which is a very good number here. It's less than 0.5, which means it's an incommensurate number that we have up here, which will be of significance later on. We'll just tell that later. So this is the time histories that we encounter. So you have fixed point LCO transition. The LCO grows in amplitude, then slowly you start getting period 1, period 2 transitions, which we are explaining up here. Already you have a period 1, period 2 transition occurring here right in the deterministic sense, and we are quantifying them that yes, indeed they are period 1, period 2 through these kilograms. And what we subsequently see at far higher flow speeds is the presence of beats, all right, where you have the behavior as shown here with very high amplitudes. You can see that they go all the way till -40 to +40 degree kind of amplitude, making the structure, the experiment itself unsafe in some sense. Now the question that comes is that you do have a beat kind of behavior, and there is a continuous exchange of modes that, energy between the modes happening, and you can see that the frequencies associated with plunge at sometimes are gaining peaks, whereas earlier they weren't. They were coalescing exactly at the pitch natural frequency. So, going by the old idea that I've been repeating few times, it is conventional in the literature to see stall from a torsional dominance perspective. Slowly, the idea of the other mode playing an important role is coming up, and we are now emphatically, or rather going towards emphatically showing that the other mode is playing indeed a very, prominent role. It is playing a prominent role. So it is not just, the pitch dominant oscillations that are going to be important up here. There is even plunge dominance coming up. Pitch dominance did not go down, but plunge is also becoming dominant. This is a very key point that the literature was missing so far on this particular part. So now, to make some sense, on what is happening and so on and so forth, we see that we have to embark, since we were having the habit of, looking into the modal interaction from synchronization perspectives, we are going ahead with the same point. We are seeing that initially the PLV values are lesser, around the, transition values to fixed point to LCOs. That is at far lower flow speeds. And subsequently, the relative phase difference increases, wherever it goes, usually beyond 0.9, it's believed to be, perfectly synchronized. But subsequently, you're getting this period 1, period 2 transitions followed by beats. To our big surprise, you see that the PLV drops from an experimental data. So now this is surprising that you start with nice synchronization and then you're losing out the synchronization for no apparent behavior. So what is the reason up for this is a question that we are asking ourselves. So there we see that we are looking at only the interaction between two modes from the relative phase difference perspective, and not looking at the contribution of the modal frequencies of these modes individually on the phase synchronization perspective. Essentially, we are now going to propose the idea that we need a frequency-specific phase synchronization, which is, in some sense called mode splitting, not exactly the same way, but there are high and low frequency components present in your same signal, and looking at just, the averaged frequencies interaction is not enough to suffice or to describe what's happening up here. So we go towards casting our signal. We are splitting our signal into high and low frequency components, and we see that high frequency components are always period 1 LCOs, showing that there is indeed pitch dominance. The belief in the literature continues. Where we bring about a change is that the low frequency components have amplitudes far higher when we go towards the beat kind of phenomena, which essentially shows that there is a plunge dominance coming up, and a canonical synchronization, those synchronization itself gave us so much insights about stall flutter. This frequency specific synchronization is giving us even more insights about stall flutter and the dominance of other modes which are usually ignored in the literature. So this particular aspect of our work was recently published in Nonlinear Dynamics, and it's a large work that I'm showing up here in brief. So if you're interested, please have a look at it and we can discuss over. So based on this, what we came to understand is that, this is up.
To conclude.
Yes, I'll conclude, please. So what are the salient findings up here is, at the chosen set of parameters, we do have a subcritical half bifurcation where a transition to stall flutter occurs. And you do have an intermittent phase synchronization at fold point followed by a perfect synchronization post the half bifurcation point. We had in a numerical study already shown that stall occurs via suppression of natural dynamics, because we said that the definition itself needs a recasting and it occurs via suppression of natural dynamics, and we are re-showing that up here through experiments. And we showed that noise-induced behaviors gives rise to also phase slips and phase flips. And we show that certain parameters play a very sensitive role, so much so that not only synchronization explains, you need a frequency-specific synchronization to specifically explain this, behaviors happening in this particular engineering system, this being a nonlinear aeroelastic system. So we feel whatever we have here would be very useful towards design and safety operations for these kind of structures. So thank you so much. Yeah.
Yeah, the floor is open to questions.
Grzegorz Litak from Poland. I just want to ask you about this stochastic excitation. So do you mean that the wind is stochastic, or some the source of vibration, the cause of vibration is stochastic? Yeah.
So I'll answer that. See, a wind tunnel. I'll just give me a second. I'll go back to the particular slide up there so that it's easier to explain.
So what is the source of this stochasticity?
Yeah. So the thing is, in a wind tunnel, say for example that I have here, this is called the suction chamber. All right. So air is sucked in, and you have a series of honeycomb meshes that makes the sucked air behave laminarly, in the sense free of fluctuations. So you get free, undisturbed deterministic flows when you suck air and it is thrown out. All right. What people do is they come up with gust chambers and so on to give rise to known amount of stochastic gusts. What we rather do up here is, instead of sucking air, we blow air, which essentially means you're having air pass through without the honeycomb meshes, so there is no way to make it streamline into a deterministic behavior. So that's why it's called a fan noise. So it's equivalent to having a ceiling fan and you have a airfoil here below you, and it vibrates because of the ceiling fan. So now that's a real noise. And how do we quantify the noise? We measure the data. We have measurement of the flow data that shows that over a mean value it fluctuates. It fluctuates rather randomly.
Okay, thank you very much.
Yeah.
Any other questions? Yeah, so otherwise, so you are working with experimental data, right?
Yes, yeah.
So you discussed about certain bifurcations in between, right?
Yes.
I wonder, how do you do the bifurcation analysis with the experimental data?
So once we acquire the data, we take the peak values for it and plot it through with respect to the bifurcation parameter, here being the flow speed.
So that shows you the type of bifurcations?
Yes. So here, since it's only a fixed point to a limit cycle transition, it's not so hard to do that. Suppose we were encountering period 2 or chaotic kind of behavior, there it would have been very hard to do that. There we would need a little more care in doing that. Here the peak values itself suffice.
So just oscillatory to steady state, that's the bifurcation.
Yeah. So once you have a limit cycle behavior that say varies between -a to +a, take that up, take those data points and plot with respect to
fine. Yeah, thanks. Thank you very much. So
you are not doing any numerical study for this?
He's doing it. He's going to present a poster tomorrow.
Okay.
The problem with stall is it is a multi-step process, and there is 2 debates on the literature. One, whether this dynamic stall model that you do numerically depends on Mach number based parameters, and you don't have it available for all regimes. The second is there is an even bigger debate, and I have been a part of it in writing a paper. that the events associated with dynamic stall are called as piecewise smooth. Alright, so they give rise to discontinuity induced bifurcations in MATLAB, numerical codes that you do. But seldom we observe that in experiments. So there has been questions asked by us that do we have this abrupt process indeed model as DIB's discontinuity induced bifurcations, or is it otherwise? So since this debate itself is not over, the idea of numerical model and capturing it is going to be a big headache. That's why we go for taking our own data.
Yeah, so if there are no more questions, let's thank Venkatramani and all speakers of this session.